there. So today let's start with another very important function in the study of complex functions, which is the complex exponential. And so the complex exponential, we write it as wz equals e to the power of z, where z is x plus iy. Now there are different ways of, and e is the exponential symbol, and now there are different ways for motivating or introducing the complex exponential. So let's just get started with one of the methods, which is we think of the complex exponential as a natural generalization of the real exponential, and therefore what we'll seek to do is we'll extend some of the properties that we're familiar with for the real exponential, and try and define the function e to the power of z such that this function carries over or borrows some of the properties that we know for the real exponential. Or in other words, we postulate that this function will satisfy one of the properties that it satisfies is that e to the power of, let's say, z1 plus z2, where z1 and z2 are two complex numbers, is e to the power of z1, e to the power of z2. So we'll postulate that if a complex exponential exists, it will have this property. The other property is that the complex exponential will be an analytic function, and so we can define its derivative. And in particular, what we want is that the derivative of the function e to the power of z with respect to z is again e to the power of z. So if you recall, this is just a natural generalization for functions of real variable, where let's say you have two real numbers, x plus y, then e to the power of x plus y is e to the power of x, e to the power of y, and we know that d e to the power of x dx is e to the power of x. So we just postulate that the complex exponential borrows these properties, and this is the way we are introducing or defining the complex exponential function. But now we can work out some consequences of this. In particular, let's look at property 1. What this means is that given e to the power of z, so from 1, given e to the power of z is e to the power of x plus iy, we can decompose this exponential and write it in the form e to the power of x, thinking of x as z1, and e to the power of iy, thinking of iy as z2. And therefore, the complex exponential can be thought of as the real exponential e to the power of x times e to the power of iy. Now, we are already familiar with properties of this function, and so what is important for us to now understand is how does this behave. So what is this? What is e to the power of iy? And for this, let's turn to the second property that we postulate and work out what e to the power iy is, and that will give us a complete definition of the complex exponential, the way we are defining it. So the second property, according to the second property, what we want is that the derivative of the exponential, complex exponential, is again the complex exponential. So let's focus on the case when let z be simply iy. So let's assume that the real part is 0, and let's just focus on this case, and therefore the derivative will give us d e to the power of iy, the derivative with respect to z, but z is also iy, should be e to the power of iy, right? But I is just a constant, so we can take it out of the derivative from here, and since it's so it comes out in the denominator here, and then we can multiply both sides by I, so it cancels from here, and what we have is that d e to the power of iy, derivative with respect to y, is I e to the power of iy. And this is quite reasonable, because if you recall the real exponential, if we have a function, let's say f of x, which is e to the power of kx, where k is some constant, then the derivative of the function with respect to x is simply k times e to the power of kx. And this is what's happening here. Here we typically do it for k being real, but given the way we're defining it, what this tells us is that it works out, the same formula works out if we think of k as the imaginary unit I. So in other words, d e to the power iy, if you differentiate it with respect to y, we'll get I times e to the power iy, and you can think of I as just a constant appearing in this function. Okay, So we have d, the derivative. Let me write it again. So from here we find that d e to the power iy dy is I e to the power iy. Now let's differentiate it again, and this will give us d2 e to the power iy dy2 is the derivative of this with respect to y, and again I is a constant, so d dy e to the power iy, and again the derivative of e to the power iy with respect to y will give us another factor of I, so we have I square e to the power iy, which is minus e to the power iy. So we find that there is a second order differential equation, which is so we have a second order ODE, second order ordinary differential equation of the form d2 iy dy square is minus e to the power of iy. If we define a function, let's say gy, which is e to the power of iy, then the function gy, which is e to the power iy, satisfies the differential equation d2g dy square equals minus g. Okay. Now this is a very familiar second order differential equation, and in particular a solution for this equation can be written in the form gy is some constant times cosine of y plus another constant times sine of y. And we can check that this sort of ansatz indeed satisfies this equation, because if you differentiate this once, then dg dy is minus a sine y plus b cosine y, and if you differentiate it once more, then d2g dy square is minus a cosine y minus b sine y, which is indeed minus of g, and therefore this ansatz satisfies this differential equation. Okay. So a solution for this differential equation is a cosine y plus b sine y, and here again gy is, we postulated gy to be e to the power iy. Now we need to figure out these constants, but notice that g evaluated at 0 is e to the power of I0, which is e to the power 0, which is just 1, right? And if we differentiate this once, then dg dy is I e to the power iy, and if we evaluate this at y equals 0, then this is just I. So these two, g0 is 1, and the first derivative with respect to y is I, evaluated y equal to 0, gives us two conditions to determine these two constants. So let's plug them into this equation and find out what these constants are. So the first condition is that g0 is 1. So let me just write down these conditions here, that g of 0 is 1 and dg dy at y equals 0 is I. So if you plug in the first condition here, then 1 is a cosine 0, which is a, plus b sine 0 is 0, and therefore this is just 0 and gives us a equals 1. If we differentiate this once, then dg dy is minus a sine y plus b cosine y, and then if we evaluate this at y equals 0, the left hand side should be I. So I is, and again at y equals 0 this factor goes to 0, cosine of 0 is 1, and this gives us b is I. So we have a is 1 and b is I. So together we find that gy, which is e to the power of iy, is a is 1, is cosine y, and b is I plus I sine y. And this is a very famous formula known as Euler's formula, which expresses a relation between the complex exponential e to the power of iy in terms of elementary cosines and sine functions. So it says that e to the power of iy is actually cosine y plus I times sine of y. So this is a very useful formula to remember. And so in the next parts of the videos, let's make use of this formula to see to work out some other interesting features that that come about, and how to use this formula in some cases. So see you there. Thanks.